So this is example number 3 on fatigue helical compressive springs. In this particular example, we're going to use the same example from problem number 1. This particular spring is preloaded to 50, and it's going to be fluctuating between 110 and 150. So what we are basically saying is, let's consider we have this spring here. We got this spring. We got your spring. And we're going to apply some load to the spring initially. We're going to apply 50. And from 50, then we're going to fluctuate this. The working load is going to be 110 and 150. So from this point, we're going to, this is 110 and this is 150. So what we are saying is, you had a baseline here you had the baseline here at 0 load. Then you had a preload applied to the problem, and then your structure is going to be fluctuating between 110 and 150. This is your fluctuating load. Okay, and the problem also says that between these two loads is fluctuating at a dynamic deflection, and that's dynamic deflection is equal to 1 inches. The problem is telling me is pin, this cold drawn, the type of material, and is squared and grounds. This is for stability purposes, and we are starting with spring index 8. So the problem, we know that your exciting frequency is 1000 RPM, and the expected life for 10 years for one shift operation is required, and C is equal to 8. And basically what we want to do is we want to find the D. So the best guess in this type of problems is, let's go in for the initial guess. Let's start with, for your initial guess, let's start with the results we got from your static analysis. Okay, that could be a good starting point. So in this particular problem, the first thing we want to know is what type of life we have. So we will start by NF. NF, we know that is 1000 RPM, so revolutions per minute. And this is 60 minutes. We have 60 minutes in 1 hour. We have 40 hours, a continuous work of 40 hours in a week. We have 52 weeks in 1 year. And this is going to be working at 10 years. It's going to be working for 10 years. So when I evaluate this gives me 1.2 times 10 to the 9 cycles. And basically this is NF is bigger than N to the 7. So we have to design for infinite life. Okay, so what we are saying is that's equivalent, your Goodman stress, equivalent stress, has to be less than your endurance stress. Okay, so we move on. The next thing that we have to do in the problem is, next item is to apply your load factor, 1.2. The problem doesn't state anything, so we would just apply the standard load. So you know that your F maximum is going to be 1.2 times 150. So the load that we will be using for analysis is 180 pounds. F minimum would be 1.2 times 110, this is 132 pounds. And then Fi is going to equal to 1.2 times 50, and that will give you 60 pounds. Okay, so these are the loads that we use in our analysis. And the next thing we want to do is, as we move on, we want to find, again, we're going to start with your static, and we want to find the material properties. And you can see that starting with this, and using the same from your static analysis, we just find this guy here. And then this is new. This you need to evaluate for fatigue. SUS 0.67 times UT. So you do that, you find this is 122.67. And the yield strength will be 0.45 times this. Comes from the static analysis. Remember, this number can change. So that's the values that we get. So we have all the data that we need. And now what we're going to do is we're going to go ahead and we're going to calculate this for your maximum. First, we're going to check your maximum fatigue. Do your fatigue check. So what you basically do is check your mean. So I'm going to find what your F alternate is and F mean is. Your F alternate will be, let me write it down, 180 minus 132 divided by 2, and that would give you 28.80 pounds. F mean will be 180 plus 132 divided by 2. That will give you 187.20 pounds. Then from here, I can find what the value of my tau A is, my tau M is. Using for this particular problem, evaluating, I can use this KB. A times FA, C was equal to 8. I have my diameter, so this gives me 58 KSI, KB 8 FMC pi d squared. This gives me 75.29 KSI. And then from here, I can find what my S maximum is. This is actually equal to your SSM. This is equal to your SSA. S maximum would be SSM plus SSA, and that gives you 86.87. And the static check just shows you that this fails because this is bigger than 82.38. So it is not satisfied. So we need to go and check your gauge and look for the next item, next gauge up. To do that, you can see that we started with this, and this value did not work. So now we go to the next diameter and we do the check. Okay, so we do the check for that, and we find your new material properties with your new diameter. And you have a MATLAB code that actually does this, but you have to change these values in your MATLAB code, by the way, okay? Those values cannot be general. And there is a small mistake here. This should be 0.190. Okay, but the answer is correct. So you got these values here, you got these values there, and you find those values. And then when you do your check, you can repeat your entire analysis again. And if you do, you need to repeat this check again. And we're just going to go ahead and give you the answers. If I did that, you can show that this is good. So it does pass your static check. So now it does your static check. we need to go back and we need to do your mechanics of your spring. Okay, to do that, what I'm going to do is that we're going to save ourselves some time here, and this is just from static analysis. So using d equal to this. So doing the analysis, sorry about that. So using d equal to 0.2625 and c equal to 8. You need to find your spring mean diameter. That's 8 times 0.2625, and this is equal to 2.1. And this is the spring rate is delta F over delta Y. So we find the spring rate, and from here we can find the active number of coils. And you can see the active number of coils exceeds. And if we cannot exceed, it has to be within the range, so this is not going to work. So what do we do in this case? Well, I cannot, so that means if I make this diameter any higher, right, making the diameter higher makes this number even higher. So that's not an option. So the only other option that I have is I cannot increase this. I cannot necessarily increase this. Then I'm going to try what happens if I increase this to 9. So I'm going to go this one up. We could also just do a combination of changing C and changing D. Increase this, but I have to also increase this and keep doing the combination until I'm happy. But let's just try C equal to 9 and see what happens. So we did this analysis, and I'm just giving you the answers here. And for C equal to 9, you can see that these are the answers that you get. And what you will see is this is all, you find your D, you find your K, you find all your deflections that you need. Then you move on and you find you will find that your NA, your active number of coils, when you find it, you see this is 9 now. This is what changed. And I found that this is equal to 10.69, and I have to go to the nearest 1/4. That would be 10.75, and this is within the range. And the number of active coils, if we go to table 10.1, you will find it gives you Na plus 1 for square ground ends. Remember, this number can change and can be different for different cases. You need to go to the table and double check that. Okay, 1075 plus 2 and gives you this value. Okay, so now that we know that this is the mechanics is correct, now we do our static analysis, a pure static. And to save us some time, again, this is supposed to be previous material. So let's go ahead and calculate this for your preload at 60. So when I have 60, this is going to give me 22.98. And you can see that this is actually bigger than 1, so this is acceptable. I'm going to safety at the maximum working load. Then this is also shows me this is acceptable. And what happens at shut, to evaluate that shut, I need to go back to table 10.1. You evaluate this at 10.1 and you find all this, you need to find your LS, L sub 0, and find it and shut. This is nothing else than Y total, just remember that. And then F shut is Y total multiplied by K, and this gives you this value. Find your stress at shut. It's the same equation. So this shows me this is good. So there's a problem. Is just saying statically my problem is safe. There's one more check I need to make sure that it has to be safe, and that's for stability. I need to check for stability, And if we do the stability, we see that it is also safe. Your your critical length. This comes from table 10.2. It is steel, and this has come from problem number 1. So we show that we could use this equation. Be careful whenever you use this. It's only good for ground ends and steel. So if I did that, I find this at 12.46, 48, and you can see that my free length is 7.27, my working Y is 3.75, so it's not going to buckle at all, so we are completely safe. So now that we are done with static, check number 2, now we move to check number 3, that would be your fatigue. To do fatigue analysis, remember, we need to find our loads to do your SN diagram. To do your SN diagram, we need to find these values. We need to find what your FS is. We need to find FS at 10 to the 3, 10 to the 7, 5, 7, and 6. And your problem stay, if you look at your problem, it said it was, if you look at the problem description, let's go back up here. This is 227, okay? And then you come to the table here and you say, well, I don't see that value there. The value is not there. Well, this is a steel alloy, okay? So we can actually use steel alloy. So there's a comma missing there. So if it's a steel alloy, I'm still accepted. I can use these values, but this is not applicable here. So, and I'm working for the case of pin. So these are the values I'm going to use for 10 to the 5, 10 to the 6, 10 to the 7. You can see those values and the calculation give me these values here, okay? So if I did that, we can start plotting this, and your plot actually is going to look like this. This value, you could put there, if you wanted to, you could put this 10 to the 0. This is your SUS, but we really start at 10 to the 3. And 10 to the 3, you have a value here. This is your first value, FS, and that would give you one straight line from there to there. Then you go to the next point, 10 to the 5. I'm going to get a value. So we go here. This value is 108. This value is 85, and 83 is the next one. So this is 85, maybe somewhere here. And then 10 to the 7. You can show that this is almost in the same point, but a little bit below. So your SN diagram for the spring is going to look something like this. And anything beyond this point, this is actually infinite life. And this is what we are looking for, okay, infinite life. So this is kind of what your diagram is going to look like. Okay, so now that we have all this information, what we want to do is we want to go ahead and find your SE, right? SES. What would that value actually be in this problem? So when we do this, first of all, I am going to assume that your K infinite is equal to 1. So we're going to assume that we are working at room temperature. We have 50% reliability, and there is no corrosion, okay? No corrosion effect. Okay, so, and then let's do 2 different methods just to show you how this works. That's method number 1. We're going to use for the case of pinned, and the pin tells you that SSEW is going to equal to prime is equal to 67.5 KSI. And then from here, you can show that SEW will be K infinite S as EW prime, and this is equal to 1, so we get the same value. Okay, and then we want to find the fully reversed endurance limit. That would be equal to zero point 0.5 S as EW SUS divided by SUS minus zero point 0.5 SEW. We got all those values, so we can plug them. It's all in detail given in the handout that's available for you online. That gives you 48. So I get a SE value of 46. And then just to show you how the method works, let's go to method number 2. This is the one that your book discusses. And your book discusses and says, look, for the P in the case, let's use SSA prime of 57.5 KSI. Let's use SSM for 77.5 KSI. And then from here, knowing that K infinity is equal to 1, we know that SSA is equal to 57.5 and SSM is equal to 77.5. Okay, then we use your Goodman intercept for a fully reversed case. So use this equation. Um, SSU, if you plug in all the values, you find this is equal to this value. Um, and so if that's the value that you get, then you want you to compare this value with this value. You can see that this is actually more conservative, right? So then this value. Particularly for this example, we will just stick with this value for rest of the exercise because it's more conservative. For your homework, for any other application, please use the methods in your textbook. Um, that's what you will be required to do. So now that we have that, we can proceed and calculate your stresses. So in your problem, you have tau max. Tau max is KB times A times F max C over pi d squared. And that gives you 68.94 KSI. Remember, I had to divide by 1,000 to get the KSI. Minimum is KB times A times F minimum times C pi d squared, and that will give you 50.56 KSI. And just don't forget that your tau I, we calculated what your tau I was, and that had a value of 22.98 KSI. Then from here, you can calculate what your SSE will be. This is used equation that's given in your handout. It's way more convenient. Minus your preload divided by ES. You have all these values. Please note that now these values are actually the values that you get up here, okay? Just give me a second. These values come from here, okay? From here, your M will be 59.75, SSA will be 9.19, KSI. Then you can these are those values here. You can see this is your SSA, and then let me change the color here quick. And this is SSM, this is SSM, and SSI, this is your SSI right here. SSI is 22.98 KSI. Okay, so those are the values that you get. And then if you replace all the numbers in here, you find that this is equal to 14.88. And this indeed 14.48 indeed is 14.88 is less than 46.81. This was SES. This is SE equivalent. So we are working with infinite life. So this check is good. Okay. So now we can calculate the factor of safety. The factor of safety in my problem will be SS equivalent divided by SSA, and that will give you 1.697, which is bigger than 1, is also acceptable. The last thing we want to do in the problem is we want to make sure that your frequency requirement is set. So for the frequency requirement, NA is equal to 10.75, C is equal to 9, and your D was equal to 0.2625. Your omega N is equal to 842, assuming both plates are attached. Okay, you replace all the numbers in here, you find this is 3700 RPM. So, and I had a forcing frequency of 1000 RPM. So therefore, omega n over omega sub 0, your factor safety for this is equal to 3.70. This is less or equal than 15, so we are good. Design meets resonance criteria, so that means that there will be no impacting between one, the springs will not be impacting each other. So as the last thing that you want to give in the problem is you want to make sure that your designer knows what your spring conditions are so they can go and manufacture it. Note again that we always want to make sure we give this to the 22nd, sometimes 64th. We also do that as well. So this concludes example number 3 on helical spring compression in fatigue.